Thank you. Okay. All right. So what I want to do today. So first of all, let me give a brief recap of where we're going formally with these lectures. Then I want to maybe talk again sort of informally. Maybe give a second introduction. Try to place try to place this whole study in context. First of all, where we're going. What the larger picture is, what our goals are, and also maybe the connection with geometric measure theory. So why is this geometric measure theory? So here's a theorem I stated yesterday. So it says the following thing: suppose I've got an integral current of dimension n-1, and it's a cycle, so it's boundary 0. It's Legendre. It annihilates the contact 1 form of the sphere bundle. It's compactly supported, and it has this funny condition that if I slice it by projections to the sphere, so that gives me a bunch of point masses, and I guess strictly speaking, so and I look at the part of those slices. Well, again, I slice it by a direction. I look for normals, so this thing is supposed to stand for some kind of object, some collection of normals, so to speak. I look at those places where the normal lies in direction v. I look at all those that lie in a certain half space. Basically, I cut off. I look at direction v. I cut off above a certain point. So here's v. I cut off above here. So h minus v t. I add the multiplicities like that, and suppose all those multiplicities are always, or at least almost always, 0, then that ensures that the current itself vanishes. Okay? So as I said, that has a companion theorem. I'll state it also in this vanishing sense, and then I'll state the positive results I'll take as corollaries. So theorem B. So now suppose I've got a current, say now it's an n-dimensional current, say inside the cotangent bundle of Rn. Or indeed, as it turns out, in this case, I can substitute any, say C2 manifold, M. And the following properties are satisfied. First of all, again, it's a cycle. Second of all, it's Lagrangian. So here, omega is a symplectic form. So as you may recall, every cotangent bundle cotangent bundles are the canonical examples of symplectic manifolds. They carry these beautiful symplectic 2 forms, and these things are supposed to annihilate them. Okay, we'll talk more about this condition in a minute. What else? Again, maybe if I look at say compact subsets of Rn, and suppose I restrict it to those guys and take the mass. Suppose these are all finite. What else? And finally, for almost every x in Rn, if I slice t by the projection to Rn at x, all those slices are 0, then t is 0. Okay, so these are the formal theorems that are somehow at the root of this approach. Okay, so again, so what are the corollaries? So corollary A basically says if we replace, I'll call these A1, A2, A3, A4, say B1, B2, B3, B4. Okay, so replace A4 by, well, let's see, maybe if I take this number, T, slice T, P, V, restrict to this upper half space, and say maybe it's the Euler characteristic of some set. I called it A yesterday. I can't really do that now. I'll call it X today. And this is true for almost every V and T. that this determines T uniquely. Okay, again, maybe I'm suppressing sort of these kind of weird questions about, well, what's this set look like anyway? How am I ensured that these Euler characteristics are well defined, etc.? Well, suppose they all are, and this is true. Well, then this is clearly a corollary. Okay, and likewise. Yes, I'm sorry. So X is some subset of Rn, say compact. Okay. Okay. So this is and then we call n of x to be this T. Okay. That's the normal cycle of T of x. Okay. The uniquely defined thing. Okay. So these things exist, relatively rarely. So yes. Tell me.
I can't really see how this is a corollary of this one.
Yeah.
Why is the dead constant? Why the Euler constant?
Okay, so why the Euler constant? The point is that if X is a nice, say, smooth set or a set with positive reach, say, then we can define this T, this n of x, by some other means, by direct means, essentially by some kind of tube construction, or if it's a submanifold, we simply look at the manifold of unit normals, okay, and consider the corresponding current. Well, then, if X is that submanifold, then that T, that n of x, that manifold I just constructed, that manifold of unit normals, does satisfy this particular condition. Okay, this is somehow a Morse theory condition, I like to say it's an Euler Morse theory condition. Okay, basically says that the n of x gives you the correct Euler Morse theory for almost every height function. That's the way to think about it. Okay. So then what's corollary B? So if we replace B4 by, now for some function, say W11, or maybe locally W11 of Rn or M, doesn't matter. Again, we place this by, I should call this A4 prime or something, and I'll call it B4 prime. So now I'm going to slice T by the projection to the base space at x for almost every x. And now I claim I want to specify what this is. Well, since I've chosen the function to be such that, well, the differential is defined almost everywhere, let's just insist that this be the case. Again, this determines T uniquely. And then we call D of F, that's the T. Okay? So again, as I said, in some way, this is another way of saying this is, again, if we look at the legitimate differentials of this function, okay, we'll look at, so those are defined as some set of a full measure of Rn, and look at the graph, okay. So it's some object. It's actually what I'm insisting. First of all, is that graph be itself, well, in the terminology of Delelis yesterday, it be an integer rectifiable current, okay. It'd be an integer rectifiable current. That would be ensured, for example, if this differential were Lipschitz, but that's not what we're insisting on at all. In fact, that's sort of the boring case. If this were Lipschitz, then I'm talking about a C11 function for which, again, we're essentially in the classical situation. But then what's being said is that integer rectifiable current can be somehow supplemented by vertical pieces, so to speak, pieces that are invisible to slicing by the projection, in such a way that we annihilate the boundary and it remains Lagrangian. Okay? So, yeah, so again, let me, if you have any questions, so here, here's an exercise I'm tempted to do, but I'm not going to. I'm probably better for you, and if you have questions about it, please ask me. So again, if f is say a C2 function, and t is the legitimate graph of its differential, which is a nice C1 object up in the C1 submanifold of the cotangent bundle, then it satisfies these relations. This condition being precisely the commutativity of the second partials, of the mixed second partials. Okay? So again, that's exercise 0, if you will, in this subject. Okay? Yeah. So anyway, so maybe it's a good time to talk about, again, what the, from a geometric measure theory point of view, what are we doing here? So I mean, we're studying these objects, n of x, d of f, and so the idea is to formulate some kind of second-order geometric measure theory. Okay, and well, I guess in some sense the philosophy is quite clear. Sometimes it's said that geometric measure theory is some kind of discipline in which we try to study highly singular objects by replacing them by currents or variables or whatever. Okay, typically these objects are have good first order properties. They're rectifiable. Yeah, they're rectifiable essentially. So now if we're going to study second order objects, second order quantity, second order geometric measure theory, well, it only makes sense in some way to think about these first order objects, these integral currents here or here, but these first order objects themselves represent first order objects. So the point is that this is a current that represents the differential. So the differential, which is already taking one derivative, has further good first order properties. In other words, the function itself has good second order properties. Okay, but of course we're measuring those first order properties in somehow different ways. Okay, and then of course the great thing about it, somehow is that this formalism of integral currents, the Federer-Fleming formalism, which is I guess from the current GMT perspective, I think somehow it seems like, I don't know, maybe it's somehow occupies somehow to me disappointingly small place in the attention of GMT practitioners. For me, it's like somehow this theory. I only got as far as chapter 4 in Federer. I never read chapter 5. Too hard for me. All this regularity theory, I can't handle it. But chapter 4, so-called, chapter 4 is called homological integration theory. So the theory of integral currents, the theory of normal currents, it's the part of geometric measure theory that has good, you might say, good functorial properties. Sort of fits into sort of this categorical perspective involving, push forwards and pullbacks and sheaves and whatever. It's like maybe we don't have any sheaves here, but somehow it's the same kind of approach. And so somehow what we're trying to do is exploit this connection to somehow enhance, or to expand the vocabulary of classical differential geometry to the extent that we can. All right, and that's more or less the goal. Okay, so let me having said this, let me also write down somehow what the formal technical goal of these lectures is, aside from the many asides and questions I intend to offer along the way. So okay, so let me say, so here's the theorem. So I'll bundle a few things together. So first assertion is this: suppose A, say is a inside Rn is a say compact WDC set. Okay, and I will let me not define that now, but I'll get back to that. I will certainly will define it when they come up in a formal way again. Okay? If A is a compact WDC set, okay, again, let me just say what it is. It's a weakly regular sublevel set of a difference of convex functions. Okay? Then, first of all, n of A exists. Okay, this is actually the Pokorny-Ratai part of it. Okay, so in other words, there exists a T with all these properties, x being A. And further, so that's one. And second of all, let me say B is another one. Right, I should also mention one other thing while I'm at it. So again, maybe to put this in a historical geometric measure theory context, somehow I was thwarted in my attempt to display for you the first 2 pages of Federer's seminal paper on the subject, curvature measures. Okay, so where are the curvature measures in this? So you might recall that I defined these differential forms, kappa 0 through kappa n minus 1. These are forms, n minus 1 forms in the sphere bundle that are invariant under the action of the Euclidean group. Okay, how did I get them? Basically, I got them by looking at this. There's a certain canonical map from the sphere bundle to Rn, essentially by adding x plus v, maybe multiplying v by a constant or by some real multiplier, and pulling back the volume form of Rn via this map, and then just separating out terms of various degrees. Essentially, that's what these things are. So it's not surprising that these things should be connected with tube formulas. Indeed, they are. So Federer's curvature measures, perhaps at least in the folklore of geometric measure theory, I hope today that this paper does receive some attention in the GMT community. I'm not sure. Please do have a look at it. It's a beautiful paper, as always, in Federer's work. But from this perspective, he defines these curvature measures, phi 0 through phi n minus 1, and even adds another one, phi n, associated with the set A. These are the so-called curvature measures. These are Federer curvature measures. So what are they? Say in the positive reach setting, what they are the following. We just take oh well. So if we take n of A, as I said before, if A is a set of positive reach, this normal cycle is well defined, and in fact it's even has particularly simple structure. It's actually a nice embedded Lipschitz submanifold. Okay, I contract it against this form kappa 0, so it's an n minus 1 current contracting an n minus 1 form. I get a signed measure. I push it down, and so on. This one's an exception, but it's sort of the boring one. It's just the Lebesgue measure restricted to A. It's just, in other words, it's just the volume of it just sits inside A. Okay. All right. So that's what these things are in sort of modern terminology. And I also talked about these quantities mu, and what are they? Mu 0 of A is defined to be phi 0, just the total variation of this. And in fact, I guess it's true for all these guys. So in particular, Gauss-Bonnet says that mu 0, which is now a number, is up to scale the Euler characteristic of A. Okay? All right. So anyway, so this is the cast of characters for the kinematic formula. So then, the theorem is this. If I integrate over the Euclidean group, I take the Euler characteristic of the intersection of these two guys in every possible relative position, then this thing admits an expansion like so for some for some constant Ci. And in fact, there's a local version. If I replace chi, which of course is essentially mu0, I can localize everything in terms of these measures, and there's another version. That's just going to confuse me and you, but everything sort of carries through as before. Okay, so I'm just going to stick with this version. All right. So any questions so far? Okay.
So
Yes. Yes.
You said they are measures.
These are signed measures.
Signed measures, and so they eat phi 0 a comma b.
That they eat some Borel set here, maybe, right? So typically it won't be B, but yeah. Okay.
And what's the intuition? What
Yeah. So again, the intuition. So what are these things? So again, yeah.
coefficients in the formula, or no?
So these guys here, again, when we take their total variations, they're the quantities that arise on the right hand side of the kinematic formula. Okay, and again, the classical picture again is if A is like a smooth domain, then these measures are given by integration of the symmetric functions of the principal curvatures. This one being the determinant, this one being just 1, hence this is the perimeter, and then in other words the zeroth elementary symmetric function, and the other ones the other elementary symmetric functions of various degrees. Okay. All right. All right. So one question I guess I realized thanks to excellent question, young man here. So I realized I maybe hadn't told you hadn't tried to tell you what integral geometry is, or maybe I did, but anyway, it somehow didn't get across. I mean, so again, here's like a little informal interlude. So I guess to me, integral geometry is, well, it's my whole world. But it's sort of to me it's sort of a vast thing. But nonetheless, it has maybe it has a narrow answer. Okay, so from a narrow perspective, it's the study of kinematic formulas. Okay, so now, given what I've told you so far, this is remarkably narrow because I've only shown you one kinematic formula. So what the heck? Although perhaps, in the context of these lectures, I guess the point is that somehow the idea is to try to understand the range of possibilities for sets A and B for which this kinematic formula remains valid. Okay. But while I'm at it, let me mention to you that there's actually this vast array of kinematic formulas. For example, in place of chi there, or mu0, I could put any other of the mu i's, and there's still an expansion of the same type, perhaps with indices shifted. Okay. Furthermore, such things exist in any Riemannian isotropic space G. So what do we have here? We have a Riemannian manifold together with a group of isometries. So we have the sphere bundle, the tangent sphere bundle of M. So G is supposed to act transitively on SM. So the terminology is, I think, obvious. So isotropic means every direction everywhere is the same. So given any point and any direction, and any other point in any other direction, there's an isometry in this group that takes this one to that one. Okay. So for example, the Euclidean group and Euclidean space is such a Riemannian isotropic space. But for example, another one would be another Euclidean space, but a restricted group, say the group generated by the unitary group together with all translations. That's again Riemannian isotropic. And there's a whole list. I mean, these things are classified, but that's not my focus here. Okay? And in fact, so it's a big project somehow to understand what the structure constants are, what those CIs are. And if time permits, I'll try to tell you a little bit about that at the end. So that's the narrow answer. There's also a broad answer. So what I want to say is that somehow, I firmly believe that somehow there exists somewhere in the heavenly realm some kind of generalized Riemannian geometry where the spaces are highly singular, and yet you can measure curvatures in some sense, and they make sense, but these curvatures exist as measures, okay, in that sense. And so maybe I'll just write generalized curvatures. So in this connection, there's this, to me, again, to me, it's like the most tantalizing problem in this area. It's what I call the Weil principle. Okay, so the starting point is Weil's theorem, so-called Weil's tube formula, which is one of the great misnomers of 20th century mathematics. So the so-called Weil tube formula tells you that if you have a compact submanifold of Euclidean space, then you look at a tube of small radius about it, well, that the volume of that tube is a polynomial in the radius of degree equal to the ambient dimension. Okay, big deal. So as Weil himself remarked in so many words, big deal. But the point is that so if A is a submanifold, say a smooth submanifold, then Weil proved that in fact in this terminology, if you look at these measures, which are now given by densities against the volume of the submanifold, then these things are actually Riemannian invariants. So they can be computed from the Riemann curvature tensor. So in particular, these things are gotten just from the intrinsic metric structure of the set. Okay? Now, in fact, as it turns out, in every known case, in every case where we can decide the issue, that's still true even if A, it's still true, for example, if A is just a convex set. It's also true if A is a say what I call maybe a regular semi-convex set, a regular set with positive reach, that is one for which the boundary, well, basically, maybe another way to say it is a semi-convex domain, which can be locally expressed as a subgraph of a semi-convex function. It's true there. It's also true, well, these things, there's an analogous statement here for, say, if A and B are subanalytic sets. And there's sort of this elementary and extremely unsatisfying argument that tells you if A is a subanalytic set, then again these things are intrinsic in the sense that if I have an isometry with another such subanalytic set, which is itself a subanalytic map, then these things are preserved. Okay, so somehow this is an extremely, I feel it's an extremely tantalizing question, particularly since so the sets we're looking at. Well, what question is it? So what's the question? So here, let me just be bold. So if n of A exists in that sense, then the corresponding phi I of A's are intrinsic. Okay, so how are you going to compute these things from a structure? It's sort of all up in the air. I mean, I don't know. It's just, but I think in many cases maybe not hopeless. Yeah.
If A is just some arbitrary set, what do you mean when you say intrinsic?
Okay, so I guess so basically, this would carry a certain assertion, for example, that if, so this conjecture, for example, includes the following subconjecture, that if A is connected and admits a normal cycle, then it is, say, a length space. Any 2 points are connected by a path of finite length within the set. Okay, that's as I say, a subconjecture, an easy part of this conjecture, but again, we don't even know that. Okay?
In which context
Yeah.
have people tried?
Nobody's tried except for me, and and
didn't like-
oh no, mistaken. I beg your pardon. I'm so full of myself. So so I would say there's one case, probably the most remarkable, most interesting case that's been accomplished to date, is the case of a two-dimensional convex surface, not the body but the surface. Okay, and this was accomplished by A.D. Alexandrov. Okay, he invented this whole theory, which is not that well known these days, so-called manifolds of bounded curvature. So he says in the case of two dimensions, it's possible to construct, say, the Gauss curvature measure by intrinsic means, and it agrees with the Gauss curvature measure constructed by extrinsic means. Okay, that's probably the state of the art, really. All these other things I mentioned, subanalytic stuff, regular PR sets, things like that, they're just, as they say in the computer world, kludges, just dumb little unenlightening arguments. But I would say,
So have you
yeah.
tried doing this in Alexandrov spaces? Or
In after many wasted years, I think I can tell you that Alexandrov space is sort of the wrong direction. It's the wrong direction, in my opinion. I mean, I could be mistaken, of course. Yeah. Yeah. Okay. So anyway, I'm not going to talk much about that because I don't know much about that. But anyway, I guess that's maybe an example of what I mean by, sort of integral geometry in this larger sense, which is for us, well, concretely doesn't exist, but I feel strongly that if civilization persists, then this is a question of interest. So yeah, okay, very good. So that's the end of my little general second introductory interlude. So let me get back to the main line. So I wanted to give maybe some examples of oh yeah. So again, here I guess I want to say. Stop. And say. Define these MA functions, Monge-Ampere functions. Okay, so these are the ones for which these guys exist. So anyway, for us, again, in these lectures, these MA functions, or DC functions, turn out to be a subclass of MA, are principally interesting for, because they allow us to define N. They allow us to define N. But let's just talk for a little bit about MA functions. So yeah. So first thing is that in R1, just in one dimension, in fact, a function is MA precisely when it's a difference of convex functions, if and only if it's so-called BV1. So what's this mean? So sort of all functions with derivative in BV. Okay, so it's not such a big deal. So so for example, I mean here's a nice one. Maybe here we go. There's a nice function in BV1. What's d of f? In this case, it's not so hard to see what it is. It's just, well, I mean, I guess it's 0 here, and then it just jumps down to being +1 here, and then it jumps up and then jumps down, jumps up and jumps, oh hell. Anyway, I'm going to lose track, whatever. So these are all the like legitimate derivatives of this function. And then d of f is gotten by filling in the gaps. Make it a cycle. Okay, it's easy. So basically, precisely, so this is d of f. So these are some kind of completion of the graph of the derivative. And as you know, basically, this is just a classical subject. If I've got some BV function of one variable, then its graph can be completed in this fashion to have finite length. Okay. Yeah. So another case of interest is, oh yeah, let me say, if n is at least 2, then we know that first of all, MA of Rn contains but is not equal to dc of Rn, and what else am I saying? It is to say it's in BV1 is not enough, which means that help me here. It does not include BV1. Okay. So here's a funny question. If n equals 2, or 1 for that matter, then every MA function is continuous. Okay, which is actually a question that arises, of course. But if n is 3 or higher, we don't know. So that's what I would call an embarrassing question. But I should probably get over it. It's a serious question. It's a serious question. So maybe here's another example. How about PL functions? Well, PL functions are always inside MA, piecewise linear functions. They furthermore, I mean, in fact, they're special cases of maybe so-called semi-algebraic or sub-analytic functions, and Lipschitz functions of those type are always MA. But in this case, in the PL case, it's possible actually to construct the differential cycle by direct means, and so maybe that should be fairly enlightening. So if f is in PL, you can construct d of f directly. For details about this in general, let's look at Bob Gerard has 2 papers on the subject. He does this in one of them. Let me just take 5 minutes and just show you how this works if in dimension 2. Okay. So I imagine I've got some piecewise linear, of course, continuous function of 2 variables. So that such a thing is associated with some triangulation of the plane. Okay, here we are. Okay, and it goes on. So in each of these domains, there's a certain constant gradient. Okay, so of course, as I said before, if I just look at the honest gradient map, honest differential map, it's just some integer rectifiable current. I mean, it's obvious in this case. Consists of these triangles cross product with that constant vector in each one. And then the claim is that this thing can be completed. The gaps can be filled in such a way, first of all, that we get a cycle, I kill all the boundary, and second of all, that the thing remains Lagrangian. Okay? Well, the first thing to do, we're going to do this by stages. First, I'm going to show you what the fibers are over these edges, and second, what the fibers are over the vertices. Okay? So now, the point is that say if I look at this edge, in order for the function as a whole to be continuous, we know that the restrictions of these two differentials to this edge must agree, obviously. So what does that mean? That means that, so let's do it this way. So I've got these two, so I'll call this V1, V2. This comes from 1, this comes from 2, say. All right? And so what that means is that this line segment here actually makes a right angle with this edge. Okay? Now, by coincidence, that's the same thing as saying that if I take this edge, so let's call this edge E, I take E, and I cross it, so this is inside R2, and I cross it with, say, this segment V1, V2, this inside, in principle, R2 star, these are covectors, that this thing here is Lagrangian. It's the same thing as saying that E is perpendicular to V1, V2, to this segment. Okay? That's a fact. Okay, so that's what I'm going to do. So over each of these edges, I fill in that little line segment oriented correctly so it cancels off the parts of the boundary that come from these two pieces. Okay, so I've succeeded so far in extending this off of this closed Lagrangian current away from the vertices. What do I do with the vertices? So here we are at V naught, say. At V naught, so let's look at, say, the fiber of the cotangent bundle at V naught. Okay? So what I'm going to do is, so imagine I've got this copy of R2 sitting over this guy. What I'm going to do is I want to fill in this I want to identify some kind of polygon inside here that will now kill the boundary that I've introduced by introducing all these edges. Okay? Well, the point is that in each of these edges, I've got some different little segment comes from, whoops, they're all perpendicular to these various edges. So over here, if I push them in here, basically I've got some object, I don't know, some kind of crazy polygon that crosses itself. I guess it'll be oriented. These guys are oriented. How's it going to go? Anyway, V1 to V2, I guess, in that case. All right. And so what I want is to fill in this thing. Well, the point is that just because, well, when I go around the circle, I look at these, connect the dots here, I've got a cycle. This polygon actually is closed. It's a cycle. So since the cohomology, the homology of R2 star is trivial, I can fill it in with some interior thing, and that's what I do in some unique way. Okay? So I append that to that, and then I've killed the boundary. This thing is trivially Lagrangian. It's in a fiber its tangent spaces are all equal to the fiber. Okay, so which are themselves Lagrangian. Okay? So this, I think, is maybe a good example to bear in mind. Yes? This guy? So anyway, so as you recall, step 0 was to just look at the honest differentials over all the various faces, okay? So now I want to build, so that step 1 was to connect any two adjacent ones by these segments. Now step 2 is going to be to construct some fiber over this vertex to kill the remaining boundary. So what is the remaining boundary? So I guess over each of these edges I've added a little line segment. And now, so basically I'm going to be looking at the sum of these things corresponding to these various edges. So now I take the boundary of this thing. It has one component that lives over V naught. Okay? That boundary is basically the sum of these guys. That's this polygon. Okay? And it's a cycle. I claim it's got to be a cycle. And so I can fill it in. And so I do. And that's D of F. Okay? So it's an elementary construction. Sort of makes you wonder, like, why didn't anybody think of this? But anyway, maybe they did. But this is what we got. So very good. Okay. Great. Yeah, I should say one more thing. In connection with the sort of general introduction. So, yeah. So the title of these lectures, you know, was thought out to some extent. So regularity. So I guess the point is that geometric measure theory seems like as a field, it's like obsessed with the calculus of variations and in particular regularity theory. Okay. So, but I guess what I want to contend here is that the formalism of geometric measure theory is much broader. It's much broader. You know, calculus variations is one direction. There's another direction. However, in some sense, maybe there's still key issues which have to do with regularity. Perhaps that's inevitable in this subject. Like again, the question is, you know, if you ask what the question of integral geometric regularity is, you know, what do you really need to construct these objects to have things like that happen, to have eventually, when we understand the Weil principle, to have the Weil principle hold. These things are just wider than wide open. I mean, they're too wide open in some sense. Perhaps we shouldn't even talk about them because they're too hard. But that's no fun. So anyway, so regularity. So it's in some sense there's a regularity question here. Okay, so before I go on, I want to mention one other technical device that's going to be needed. It's relatively elementary, but it's nice. It's helpful. So-called the idea of the Clark differential. Okay, so this is some nice generalization of the differential, or even the subdifferential of a convex function. So suppose I've got some Lipschitz function. Let's say we're in Rn just for simplicity. So by Rademacher's theorem, this thing is differentiable almost everywhere. And so if I've got a point in Rn, what we're going to do is define the Clark differential of f at x in the following fashion. What I'm going to do is I'm going to look at all sequences of points that converge to, let's call it x0, to x0, okay? And let's take limits of such things. Okay, look at all convergent sequences of that type. Okay, so then we take the set of these things, and we take the convex hull. Okay, so there's some convex valued set function. Okay, it's an elementary thing. If f is convex, then this is the usual subdifferential. What's really convenient about this thing is that somehow we get there's an implicit function theorem that comes like for free. So it says the following. Suppose I've got some point, and suppose that this point is not a Clark critical point of f. So 0 does not belong to this Clark differential. Okay? Then there exists a neighborhood of x and an open subset, say V, inside Rn minus 1, so that how to say this? So that U is by Lipschitz equivalent to V cross some little interval, say let's say f of x naught minus epsilon f of x naught plus epsilon. This is by Lipschitz. And so I guess, and what's more, so if I take here the projection to the second factor, and there's f, such that commutes. Okay? So in other words, if in the neighborhood of this point, x naught, the level sets are actually just nice Lipschitz hypersurfaces, and the whole thing is actually just bi-Lipschitz equivalent to this product. Sort of, it's just a Lipschitz version of implicit function theorem. And the proof is like trivial. The proof is completely trivial. So basically what you do is okay, so first of all, you note that this is upper semi-continuous set function in the sense that if I have some sequence of points converging to x naught, I take the Clark differentials there, then any limit of elements of those Clark differentials also live in here. So basically you have these small sets. Here I've got the Clark differential at x naught, here I've got the Clark differential at these approaching points, and the limits are just actually fit nicely inside there. Okay? So, or another way of saying that is that if I just smooth this thing by convolution, the derivative of the convolution, well, must lie inside this space more or less, or close to this set, just because the derivatives of convolution are just convex combinations of nearby differentials. Okay? And so to say this means that, well, if I convolve it by some small modifier, then everything's nice and regular. I can just flow by that convolved, by the derivative, by the gradient of that convolved function. Everything works. It doesn't sound like there's a problem, and there is no problem. Okay? So that's how that works. Good. All right. So yeah. So let me state one more thing while I'm at it. So here's like a companion to corollary A. So here's a proposition. Suppose I've got an MA function, and suppose it's Lipschitz. In fact, a DC function or locally Lipschitz, say. DC functions are of this type. Then the support of the differential cycle of f sits inside the graph of the Clark differential. Okay, so that's anyway. As that's actually just sort of a byproduct of the proof of this theorem. Okay, so what I want to do next is give you a brief sketch of how to prove theorems A and B. But before you do that, let's take a 7-minute break. We'll come back at the hour. Any questions? So maybe. Yes.
With my mind of calculator variation, I was wondering something about MA functions.
Yes.
How it behaves when taking limits under reasonable assumptions.
Yes. Right. So maybe I'm going to cut 2 minutes off off of our break. Okay. So I actually meant to say that up here. So that's actually yeah. So actually that's my favorite corollary here. Let me put that up here. So here's a theorem. So suppose I've got some functions, say there's C2 functions of Rn, okay? All right? And suppose that, say, they converge, say, in W11 loc to some function f naught, okay? And I want to impose a condition, or a family of conditions. And let's suppose, let's look at the Hessians of these guys. Okay, and let's look at all minors of these Hessians. Okay, all square minors of the Hessians. Okay. And let's take the determinants of these guys. And let's take the absolute values of those determinants. Okay? And finally, let's integrate these guys over compact sets K inside Rn. Duval. And we'll suppose that these guys are, say, uniformly bounded by some constant depending on the compact set K. Okay? Then F naught is MA, and D of F naught is the flat limit of the D of FKs. These things just being the usual graphs of the gradients of the differentials. Okay? All right, so let me just say how this is proved. So this is quite simple given these other facts. Okay? So first remark is that all these relations here, basically, if I look at all these things here, actually, if you think about it for a minute, if I look at this collection of these numbers as big I and big J vary over all possible subsets of the same cardinality, the sum of these things is up to scale the same as the mass of this, or the same as the mass of the part of this over K. All right. So Federer-Fleming says, well, we can take a limit of a subsequence of these guys. Okay? So we take a limit of a subsequence of guys. This limit is an integral current, but it satisfies these conditions for F naught. So the limit is uniquely defined, so in fact, it's not a subsequential limit, it's a limit. Okay? And in fact, as I mentioned briefly the other day, this is the only known method to construct MA functions. Okay? So again, here's another embarrassing question. This one again, I should get over this, but I still am embarrassed by this in some way. It's like, is it true that every MA function can be approximated in this fashion? Okay? That seems like a really hard question. I mean, I don't know how to do it, but who knows? Okay, so I promised to tell you basically roughly how to prove theorems A and B. So we don't have much time, so I'm going to be pretty sketchy. Okay, so actually, as I say, theorems A and B are actually very close. There's a little bit, theorem A has a little bit of extra geometry to it. Okay, so as I say, I have to be a little sketchy. So again, I've got this current has all those properties. Okay, so basically what the moral of the story, the basic idea is this. So the model fact. So I guess has to do with another sort of classical collection of Lagrangian subspaces. So you can find this model fact in, of all places, Harvey and Lawson's paper on calibrated geometries. So it says that suppose I have I've got a smooth Lagrangian submanifold of a cotangent bundle, and suppose that the projection is a submersion. Okay, so in other words, the differential projection has constant rank. And so then it turns out that locally anyway, there exists some k-dimensional, let's say has rank k, some k-dimensional submanifold of Rn, and some smooth function so that M is equal to, well, first of all, the I'll call it the conormal bundle of M, okay, plus df. So let me, what does that mean? So it means the following. So this thing lives inside M lives inside here. So I've got a base point, and I've got some y's here, and I've got these things. And y is perpendicular to the tangent space to v at x. Okay? So in other words, these things look like somehow perturbed normal bundles. I'm tempted to draw this picture. It's a little bit misleading because these perpendicular lines live in some other space, in the fibers. Okay? And then maybe they're shifted a little bit by this differential. Okay? So yeah, so again, somehow this is as I say, this is like maybe these guys here, these conormal bundles are themselves, maybe simpler models of Lagrangian manifolds. So I guess now we have two types, and somehow this is like a combination of the two. I told you, for example, that the graph of a differential is Lagrangian. So I guess, for example, if this is rank n, then V is like Rn itself. This is nothing. I just get the graph. And if F is 0, then I'm saying that a conormal bundle is itself Lagrangian. So again, it's just some fancy version of saying, well, these things are perpendicular to these things. I look at the tangent spaces. In order to annihilate the symplectic form, that's just some fancy way of saying the fibers are orthogonal to the base. Okay. Again, it's a calculation that's worth doing. I'm not going to do it here because I will totally mess it up. But if you'd care to do it, I'd love to get some practice with it. So please ask. Okay, so there's our model. So what can we do? So I start with my current. So there's some measure theoretic version of this thing. How can I say it? What I know is that if I slice by the projection into Rn, then I always get 0 here. So what I want to do is take a maximal, say Rk, inside Rn. So let me just say, let's look at this projection. Let me call this Q. So I want K to be maximal here, say, so that when I slice T by now Q composed of pi, say Y, this is identically 0. Okay? So I know that, when K equals n, it works. I just push it down as far as I can. Okay? So then, if I take one of these slices, and now if I slice it again by some, say, projection, say, to some coordinate function, to some coordinate plane, say xi, say at some value, say t, then this, I beg your pardon, I've got it exactly wrong. I want to say this not to be 0 for some set y of full measure. Okay, sorry, that's right. So in fact, K is going to be less than n, less than n. Okay, so if I do that, though, if I slice again by, I take some other coordinate, then these guys are 0 by maximality. Okay? So that means what? So that means that basically, so if here's my RK, the picture is something like this, that the projection, somehow by this Harvey-Lawson model fact, the projection is some, well, it's not a submanifold, but it's some nice rectifiable set, and I guess we're inside Rn. I guess these slices are not zero, but all the higher slices are zero. So basically what that means is it looks like, the projection basically looks like some k-dimensional rectifiable set. Okay, yes?
Why you said that slice is zero?
Yeah, so the point is that so I took k to be the maximal dimension for which these slices are not zero. So if I were to slice into by projection to a higher one, I'd always get zero. That's effectively what I've done here. Okay. Okay. So now, so here I guess is my virtual V. Okay. So now the point is that if I look at the tangent planes to t, so I take tan. If I could just speak. I mean, this is not a good formal exposition, so please don't hold me to it. So I look at these tangent planes. So what are they? So they basically look like the tangent planes to V plus something like the kernel of d pi restricted to the, let me call this t naught, say. I'll call this tau naught. Okay? So in other words, we're in this sort of submersive, at least tangent plane by tangent plane, we're somehow in this submersive situation. The image of the differential of projection is the tangent plane here, and then there's a kernel. There's this part. And now the Lagrangian condition well, basically, all these tangent planes have to be themselves Lagrangian planes inside the T star Rn. Okay, that's just how it works. So, but in order for that to be true, this kernel, okay, well, so this sits inside Rn star, some copy of Rn. Okay, this sits inside Rn. This kernel is, well, if I think of it as both sitting inside the same Rn, it's perpendicular to the tangent space to V. Okay? Okay. So, yeah, so what am I saying? So, yeah, so I guess what, right, so basically so now if I look at these slices, these non-zero slices, well, these are their tangent planes. These are tangent planes to the slices. Okay, so all these tangent planes are somehow, you know, in particular, they well, what's the point? I'm not doing. Right. So if I look at this guy, we're sitting over some particular point here. Here's pi of x. So here, pi of xv, just x. So there's some fiber over this thing. All the tangent planes are sitting inside Rn star. They're all vertical. And furthermore, well, this thing is so these are what? N minus k dimensional. These things are k-dimensional. They all, you know, basically in this picture, they all have to look, well, either like this or like there's some translate of this, okay? And then, well, rather than try to get this technically right, let me just continue in this vein. There's this basic fact about slicing, so-called separation lemma. So again, let me see if I can at least paraphrase it. So basically, if I've got some integral current, and suppose I've got I've got some map of the ambient space into some other space, and suppose every time I slice this integral current by some function on this target space, suppose all those slices are 0, then the current itself is a sum, or the indecomposable components of that current are sums of elements that lie in the fibers of the projection. So let me say that maybe. So if T, say, is in IK of some manifold M maps to N, and suppose, call it pi, and suppose that T F composed with pi X is 0 for all, say, F mapping N to R, then, I hope I get this right, then T is a sum of Ti where each Ti is supported inside some fiber of pi. Okay. Anyway, I have more to say here, but let me try to cut my losses and just say the following. So the basic idea is just this. So now, the fibers have only these particular, the fibers of this projection all level above this point. They're all vertical, and they're all parallel in some sense. Okay, so by the constancy theorem, each one has to live in some particular translate of Rn minus k up inside the fiber. Okay, and what's more, because the boundary is 0, they have to extend to infinity. The boundary of my original cycle is 0. So it's 0, so I have to extend to infinity. But if that's going to happen, for some set of full measure, then when I integrate up the mass using some basic facts about slicing, that's going to contradict item B3. Okay, so that's it. So in some sense, let me just go back maybe to this picture. So basically the idea is if I've got such a Lagrangian current with this slicing property, then it looks like this. But the fibers of these guys extend to infinity. So the mass cannot possibly be finite. That's it. All right? So simple. In some sense, geometrically, it's simple. Okay. So that's corollary B. How about corollary A? So corollary A has two parts. So the first part basically is just to look at theorem B again. So let's consider, I've got my SRn, so this is just Rn across the sphere. Let's cross that with another R, say, or maybe let's say with 0 infinity or something. Okay. So this here I can think of as being a copy of Rn with the origin deleted. Okay, and now it makes sense somehow to kind of switch the factors. Okay, so now I'm going to think of this manifold as my M and think about how I prove theorem B. Well, not with Rn, but with this value, this version of M. So now the point is, if I've got my Legendrian current T, so that lives inside here. So let me just take T cross 0 infinity. This now is, well, this guy here, again, I can think of as being the cotangent bundle of this deleted space. Okay. In other words, since this cotangent bundle is a product, I mean, Rn cross Rn star is also Rn star cross Rn star star, as you know. So it's somehow the cotangent bundle of Rn star, which is what we're we're just reversing the roles of these guys. And this guy here, I can be thought of as Lagrangian inside this space here, yes.
You were a little fast here. Can you say again what exactly?
Yeah. Okay. So what I want to do is apply theorem B actually. Okay. So on the one hand, in the A setting, I'm thinking about Legendrian things inside the sphere bundle. In the B setting, I'm thinking about Lagrangian things inside the cotangent bundle.
Yeah, no, I'm talking about
Here.
what you're writing down.
Yes. Okay. So let me continue, and hopefully it'll become clear. Okay. So T lives inside here. It's an n-1 current inside here. Okay. So now I'm going to jack it up by one dimension. Let's add a 0 infinity here. Okay. And then this thing, of course, I can identify with the deleted Rn. And then I'm going to switch the roles of the factors. I'm going to think of this as the base, and this is the fiber. Okay? Now, the point is that this, if I do that, I can think of this space as somehow like the cotangent bundle of this object, okay, rather than the other way around. Okay? And so now, if I apply theorem B, what's more, this current that I'm investigating, it's when I jack it up by 0 infinity, it's now Lagrangian. Okay? It's no longer Legendrian, but it's Lagrangian in the obvious sense. And so theorem B tells me that, well, I can apply the same thing. Condition A4, well, so the idea is somehow condition A4 is like a specialized version of condition B4. So but let's say what it says. So so it says that if I project by T to the projection, let's say so there's a projection here into Rn minus 0. Let me call that pi again. If I slice by pi, let me call it y to emphasize that these things are somehow coming from the fiber. If these things are identically 0, then T is 0. Okay, so again, if I just change the order of these things, multiply by this other factor, then we're in the situation of theorem B. Okay, and so that's that. Okay, however, this condition here is not quite the same as condition A4 prime. So what does this say? So I'm running out of time, and I really should try to make this point more clearly. So what I'm going to do is try to say it in very vague terms now, or at least whatever terms I can muster in the remaining 3 minutes, and I will revisit it hopefully in a better way at the beginning of next time. Okay? Yeah, I didn't tell you what I call the theorem A or corollary A. I call it the envelope theorem. So why do I call it the envelope theorem? So there's this really classical construction or classical kind of thing that in geometry, basically, you look at some family of lines, say. Well, that family of lines has an envelope. It's the family of lines to some curve. Okay? So basically what I want to say here is that, so these VTs here, what are they? Basically that's just, the sphere across the line I'm thinking of it as a space of, say, oriented affine hyperplanes. Okay? And these places where the slices occur, these are like tangent planes, tangent hyperplanes. Okay? So basically what I'm saying, what this theorem says is that if I know all the tangent hyperplanes to this object, I can reconstruct the object. Okay? So that's the geometric content here. Okay? Formally is a little bit different. But obviously, I'm not going to communicate that properly right now, so let me stop.